One thing about this is that it is not very fast. And the reason it's not very fast is we are writing not only the metadata blocks to the journal, but every file content block. There's a lot more file content that's written than metadata. Right? This can be very large. And so is there some way that we could optimize by not writing the file content blocks? And that is a different mode. So we had talked about the journal data mode. Now we're going to look at the ordered. So in the ordered data case, we only log the metadata blocks. And we have a rule that says we write all the file content blocks before we commit the associated metadata. What we're going to find is that this certainly is a lot faster because we don't have to write the file content blocks twice. However, there's a lot of care we're going to have to take. The journal data mode is very simple. It just works. The order data, we're going to have a lot of special cases we're going to need to deal with. Why do we have this rule, by the way? Well, imagine we wrote metadata first. Imagine, for instance, we write to the end of a file. And let's say that this requires allocating a new block. So we allocate block 57. And now we write hello in it. So block 57 has hello, and also our inode gets updated to add 57. In the journal data case, this was a transaction either that both of these made it to disk or neither of these made it to disk, and in either case that'd be fine. Right, so what can happen? The inode makes it to disk, so we've now got an inode that refers to this extra block 57. But the problem is the block 57 may have very different contents, right? Maybe this is some key. It certainly doesn't say hello. So this is old data that this file now gets access to from some other program. Of course, the other use we have, the other change that gets made is we have the free bitmap, free block bitmap. That shows that this block is in use. If on the other hand, we go ahead and write this data, so we now go ahead and write hello into location 57, and these guys don't make it, right? We don't get a committed transaction, then as far as the file system is concerned, we have just written some data into a free block. That doesn't matter, right? Doesn't make sense. So this ordered data mode is very common for Linux for performance reasons. But we're going to now look at some particular issues that have to be dealt with. So one example let's look at. So we do a remove directory, and then we go ahead and reuse the block. Okay, so for instance, let's say the directory, the contents of the directory was in block 68, and now we go ahead and rewrite block 68 and put in block 68 something, like hello. So what have we got going on? So what have we got changed? Let's see. So we've got a hello block that says that's value 68. We've got an inode for our file that refers to 68. We've also got some sort of what directory was this directory in. So let's look at that parent directory. The parent directory used to have a reference to 68, and we're actually going to get rid of it. So that directory entry is now empty. If this all makes it to the file system, that's great. If just these two make it to the file system, that is, this is metadata, right? So if this metadata makes it to the file system first, then we're fine. If we write the file system data first and the metadata doesn't make it, then actually we're in trouble, because what we have on disk is the parent directory is referring to now a file that contains hello when it's supposed to be some a second directory, right? The directory we removed here. So that's a big problem. So the solution is the following, and there's just going to be a number of these sort of solutions that we're going to be used, but we're not going to reuse the free block. We're not going to reuse the free block until the freeing system call has been committed. The problem here is the fact that we freed a block that's actually metadata, right, because it's a directory, and then reused it for file contents data. That's a problem. So if we just don't reuse it until it's been committed, that solves it. Let's look at problem number 2. So problem number 2 looks like this. We do a make directory. We commit. We do a remove directory. We commit. And then we reuse that block in a file. And then we commit. So let's look at what happens. Sorry, and then we crash. So let's see what happens. We have gone ahead and created a directory. So we have, let's say, dot and dot dot. That's it, let's say. So this is block 99. And the inode refers to 99. And then we remove the directory. So now all of a sudden this is freed. And then we commit. So that's important. So we're not breaking rule number 1. So what do we have in our log? We have one transaction that says 99 is dot and dot dot. And then we have, so this is transaction 1. Transaction 2 says basically free 99. And then transaction 3 we'll look at in a moment. So we do this part, right? And then we do a remove directory, which basically gets rid of this inode. And this is now free. And then we reuse this block in a file. So now we're going to go ahead and write, hello in here. Okay? And we commit that, and then we crash. So T3 has something with the, use 99. That is, the free bitmap is going to show that 99 is now in use. T2 is going to show that the free bitmap, that block 99 is free. In order for T3 to have committed, we have to have written our file content first, right? We write our file contents first. So in here we have 99 says hello. So we know that's in the file system. Now we go through and we replay these. So because we crashed. So what's going to happen? First thing we do is go into 99. So we overwrite it with dot and dot dot. And then notice we've just overridden our one and only copy of hello here. And then we update T2 to say, actually 99 is not in use. And then we update T3 to say, yes, actually it is in use. And our inode for our file now points to this dot and dot dot, which is when it's supposed to point to hello. That is a problem. Our solution is going to be, basically we shouldn't have written dot and dot dot into 99 because we know we're about to free 99 later. So we know some later transaction could have had file content that writes into 99, that this should not replay over. So the solution is we put revoke records in our transactions. So what we would actually here in T2 do is actually put a revoke 99. And then when we're replaying, we go ahead and we say, okay, I'm going to replay this write, except wait a second, if there's a later revoke, don't do any writes in any previous transactions. Both of these occurred because of the fact that we have this mismatch between sometimes we have a block that is treated as metadata if it's part of a directory, and sometimes we have a block that's treated as file content. And if that types can change, then we have an issue because sometimes it's making a log, sometimes it's not making a log. If all directory blocks were allocated completely separately from all file content blocks, this wouldn't be an issue because we wouldn't have this override. One issue comes about from a certain behavior we have in Unix in general. So let's say you open a file, right? Then it gets put in the system open file table. And it has a reference to the inode. And then you unlink the file before you close the file. So we still have a reference to our inode in our system open file table. So the contents of the file need to still be around, and the inode needs to still be around. Unlink is going to remove the directory entry, but not free up the inode. And only on a close will we actually go ahead and say, oh, we are the last open file reference to this inode, and the inode has no hard links. We better go and delete the inode and delete the associated direct and indirect blocks. However, the problem is, let's say we crash at this point. As far as the file system is concerned, we have let's say we've committed here, and then we crash before we close. What'll happen? We have got a inode that is not reachable by anybody. So the solution here is we add an inode that has no links but open to the superblock. So if this is inode number 137, we'd actually put a list in a superblock that says 137. And then when we restart, we're going to go through and say, okay, these inodes had been freed, but needed to still be around because they were parts of open files. We'll go ahead and remove those. There is one problem that comes about with disk drives. And that is, let's say, right, we talked about the fact that we write the descriptor block, we write all the data blocks, we wait for the disk drive to show that they're done, and then we write the commit block. Unfortunately, disks actually often have write caches and will also reorder writes. And so what happens if it goes ahead and caches these writes and says, oh yeah, they're done, but they're not really done. And then our commit block comes in, and then it chooses to write the commit block first. Then we've got so we've got the descriptor block there, the commit block there, but not all the intervening data blocks got written. So we've got in our log, right, if we look at this part of the transaction, we've got a descriptor that looks good. We've got a commit that looks good, right? Our sequence numbers match. So this is 13, and this is 13. But then we've got some data blocks. So this is correct data block, and correct. But this one is old. And let's say this one is, let's say that one is old. But let's say this one is old, and this one is correct, but this one is old too. How can we mitigate this against this, right? We can certainly try and make sure that the disk drive controller is set up so it doesn't do reordering, and that we can force it to write, but they don't always write correctly. So the solution is we go ahead and can add a checksum here. This checksum is going to actually checksum all the data blocks. So this checksum is only going to be valid if we have correct versions of all these disk blocks. This checksumming of the log isn't actually part of Ext3, it's part of Ext4. But what that would tell us, by the way, if the checksum doesn't match, is this is an invalid transaction. Not only would we not run this transaction, any future transactions we can't run as well, because they were all dependent on having run this transaction. So only the previous transaction would be sort of the highest transaction we could run. So you have seen Ext3 now. Ext3 is a very popular file system, and rightly so.